Okay, please start.
Okay. Yes. So this is joint work with Joseph Umbreras at CQT in the US and Andreas Winter. We are both at UAB, and we just put the preprint on archive. So what we study in this paper are linear models of stationary stochastic processes. So I will start by defining what this means and giving some properties of these models, and in particular mentioning an interpretation of these models in the context of general probabilistic theories. So once you have such interpretation, you can ask which kind of theory supports these stochastic processes, and it could be a classical or quantum or a general exotic model. And so an important question is to understand the differences in expressive powers of these classes of models. And so after giving the necessary background, I will show a sketch of the proof that quantum models are in fact insufficient. So let me start from the definition of stationary stochastic processes. Here we consider an alphabet with a finite number of symbols and the set of all possible words of arbitrary length, including the empty word epsilon. And we focus on stationary processes. That is, we can assign a probability to any word, and it does not matter to which time we start caring about the word. And so this is the stationarity property. And for the empty word, we have that the probability is 1. And so the question is, can we find an explanation of a stochastic process? So a very simple example of how to get and a familiar for you probably example for how to get a stationary stochastic process is to consider repeated quantum measurements on a system with the same instrument. Here, an instrument is described by a set of maps, the U, such that their sum is unital, and the probability of a sequence of outcomes U on the state row can be computed by the appropriate Born rule. And going through the Heisenberg picture, then we can rewrite this with this notation, which is convenient since we can read the word from left to right. And taking rho to be a fixed point of the sum of the maps, this probability defines a stationary process. So this notation can be pictorially represented with this diagram, where we see that we start from a state pi of a hidden memory system, which evolves to maps labeled by the outcomes that we get at each step. And after we get the last symbol, we take the inner product of the hidden state with some other right stationary vector. In the case of quantum models, this tau, this right vector, will be the identity. But now we can abstract from this and forget about the particular requirements for quantum evolution maps, which are CP maps. And if we just insist of requiring this linear structure and this compositional structure of the maps, then we get what is called a quasi-realization of a stationary stochastic process. So a quasi-realization is defined as a quadruple of a real vector space, a vector in its dual, and the function from words to linear maps in the vector space, such that the empty word is mapped to the identity, and the product of maps associated to two words is the map associated to the word obtained by juxtaposition. And moreover, in order to enforce stationarity, we ask that pi is a left stationary vector, is a left eigenvector of this map, and tau is a right eigenvector. And the probability would be computed in this way, which in fact respects the structure of the picture that we had in the previous slide. So these kind of models have very nice properties, and in fact, they are quite general explanation of a stochastic process. It can be proved that a finite dimensional quasi-realization exists if and only if the rank of a certain matrix constructed from the probabilities is finite. Quasi-realization of the same process are called equivalent. Quasi-realizations with minimal dimensional view have a special role, and they are called regular, and they are related to each other by similarity transformation. The function from words to maps is given entirely by the single letter maps, making a quasi-realization specified by a finite list of real numbers. And most importantly, there exists a canonical procedure to obtain a regular representation from the knowledge of the probabilities and just linear algebra. So if you want to see more about these properties, you can see the review by Vidyasagar. So the problem is maybe that just asking the structure of that we mentioned for quasi-realization is not enough to define an actual stochastic process, because if you consider an arbitrary set of matrices, you do not have the guarantee that probabilities are non-negative. Instead, if you restrict to models based on classical or quantum dynamics, you have this guarantee. So if you restrict to classical models, then you have what are also known as hidden Markov models, where the hidden state is a probability distribution, which evolves through matrices with non-negative entries. These are also called positive realization. And if you consider quantum models, as I mentioned, you have hidden quantum Markov models, where the hidden state is a quantum state evolving through completely positive maps. And these are also called completely positive realizations. However, even if you don't have such interpretation of the stochastic process, there is still some nice geometric feature that quasi-realization associated to stochastic processes have. And in fact, it's immediate to show that the quasi-realization defines a non-negative measure if and only if there is a convex cone inside the vector space, which is without loss of generality closed, such that tau belongs to the cone. The cone is invariant under the maps, and pi is in the dual of the cone. And we call cones with these properties stables. And in fact, it's hard to check if given a candidate quasi-realization, if this cone exists, it's in fact undecidable. Nevertheless, if you know that such cone exists, then you can have an interpretation as a general probabilistic theory in the context of general probabilistic theory. Here, you would need a cone and a dual of this cone to define a state space. In this case, the state space are the elements of the dual cone, which are normalized through the unit tau. And we also need to define an effect space that gives probabilities which are actual probabilities, so between 0 and 1. And you can do it if you have a stable cone. And then the maps are in fact linear maps on the state space. And at each step, the state gets transformed by this linear map, and the state after the outcome u at time t+1 is obtained by the state at time t, acting with a map du and divided by the probability of getting u. In general, this interpretation as a general, in the context of general probabilistic theory, is not unique, in the sense that a quasi-realization does not immediately identify a unique stable closed cone. But we can put inner and outer bounds on the stable cones from the cones generated by the quasi-realization dynamics. So what can be shown is that any stable closed cone has to satisfy this inclusion. It has to be larger than the cone obtained from the orbits of the right stationary state. and actually its closure, and it has to be smaller than the dual of the cone generated from the orbits of the left stationary state. And so we cannot say much more at this point. So if instead you have the guarantee that there exists a classical or a quantum model for your process, then you also have the guarantee that there exists cones with some nice, with some peculiar properties. So already in the early days, it was shown that a necessary and sufficient condition for a positive realization to exist is that there exists a polyhedral stable cone. For the quantum case, there is an analogous characterization in terms of necessary and sufficient conditions given by Monras and Winter, where it's highlighted the role of semi-definite representable cones. And setting this necessary condition, sufficient condition is much more complicated. And for our purposes, what is important is that a necessary condition is that there exists a stable SDR cone. So in particular, these cones are semi-algebraic, that is, they can be defined through a finite number of inequalities involving polynomials of the coordinates. And so here we see a possible attack to show that quantum models are not enough, which is the one that we follow. And it is to search for quasi-realization of stochastic processes where the only stable cones are not semi-algebraic. So before going to the actual proof, let me define the question a little bit better. So we want to understand how expressive are classical and quantum models. So we can define three subsets of stationary processes. So G are the processes which admit a finite quasi-realization. P are the processes with a positive realization, so a classical one. CP are the processes which admit a completely positive realization, so a quantum one. So clearly they have to respect these inclusions. And these inclusions are in fact strict. So P is strictly included in G was proven in the early days by Fox, Rubin, and Darmadikar and Karno. And P is strictly included in CP was proven by Monras and Winter, and we prove the last statement. So is it actually instructive to look at how P is strictly included in G was proven? Because they initially, the processes they consider were initially defined as functions of infinite dimensional Markov chains. So in this case, the state space is the set of non-negative integers. So the state can be one of these non-negative integers. And what happens is that at each step, if the state is in zero, at the subsequent step, it's in the state L, with this probability for L larger than zero, and which this probability is so exponential in L, and multiplied by this trigonometric function. So when L is not in zero, with probability 1, it goes to the lower state. So from L, it goes to L minus 1. And then the process is generated by taking a function of the current state of the hidden memory. And the symbol that is output is A if the state is in 0, and B if the state is in X. So the key ingredient to show that there is not a classical realization for this process is that the eigenvalues with maximum modulus of a non-negative matrix have phases which are commensurate with pi. And one can tune alpha in such a way that it is not commensurate with pi, and this would imply a violation of this fact if there was a classical realization, a positive realization. So this approach fails in the quantum case because the spectra of CP maps do not have similar restrictions. But it was not known if this process could have a quantum realization or not. And this is why we started considering these processes. But we found out that, in fact, quantum realization exists on a Q-treat. And this is very interesting because it tells us that hidden quantum Markov models are quite powerful. This is an example of a process which was defined not in a quantum, not starting from a quantum interpretation, but in fact, it has a quantum model. And this class of quantum models that we can find are even more general than the FRDN processes if one does not tune the parameters exactly to produce those processes, but even for different choices of the parameters, they do not admit classical realization. And in fact, so this is a bit of a lateral point, and I will briefly comment on it. If we consider a choice of parameters where the models are actually qubit models, we can consider a noisy version of the process. And we show that the gap between the classical and quantum memory requirements is even robust if one perturbs the maps with the polarizing noise. In the sense that the number of states of the Markov model must grow with a power law in terms of the noise parameter. If you want, I can tell you more about this. But let's go back to our main question. So the approach based on the spectral properties of the map does not go anywhere in this case. So we set out to follow the other approach, which is a more geometric approach, which was used by Monraz and Winter to prove the separation between classical and quantum models. So there, they proved the non-existence of polyhedral stable cones by exhibiting a suitable symmetry that the cone must respect, but which polyhedral cones cannot have. So the question is if we can find a similar restriction to exclude the existence of stable SDR cones in some quasi-realizations of some process. So there is an important difficulty is that a suitable closed stable cone can be in principle any cone between Cmin and Cmax. But this simplifies this Cmin is actually equal to Cmax because then we have just one possible candidate. And this is the idea that we follow. A convenient fact is that if it is sufficient to prove the non-existence of SDR suitable cones in a regular quasi-realization because all the quasi-realizations are related by a linear transformation. Okay, so in the end, what we found out as the simplest example is to construct a quasi-realization over the exponential cone. So the exponential cone is a three-dimensional cone defined through inequalities which involve the exponential function. And in fact, it can also be seen as the cone that one obtains by taking the graph of the exponential function at x2 equal 1 and intersecting with the raised from the origin and taking the closure. The dual of the exponential cone has a similar structure, in fact, and it also can be obtained by taking the graph of an exponential function, this time at y3 equal minus 1, and taking the race that intersects it. And so the simplest example that we have, it's actually a model based on an alphabet of 3 letters. So we need 3 maps. And we find this parameterization of these 3 maps, which is such that there exists a choice of parameters which give such that these maps are such that their sum is unique and left right eigenvectors with eigenvalue 1, which we can call pi and tau. And the resulting quasi-realization is in fact a good quasi-realization of a stochastic process. And the exponential cone is the unique stable closed convex cone admitted by the quasi-realization. And therefore the resulting stochastic process do not admit a quantum realization. So the steps are, first of all, to show the existence of the process. And here we first choose D0 in such a way that mu0 transpose is in the dual of the exponential cone, M0 is in the exponential cone. And with this choice, D0, D1, and D2 are such that they preserve the exponential cone acting from the left and the dual cone acting from the right. And choosing mu appropriately, we have that a unique tau in the exponential cone and pi in the dual exist such that they are also stationary. And the key ingredient here is a generalized Perron-Frobenius theorem, which says that if a matrix leaves a cone invariant, then it admits an eigenvector in the cone with eigenvalue equal to the absolute value of its spectral radius. And so these three ingredients certifies us the existence of a stable cone. So the probabilities that we can define from this quasi-realization are in fact non-negative. And we have also the first inclusion that C mean is inside the exponential cone and the dual of C max is inside the dual of the exponential cone. Now we need to show the other inclusion. And we do it by looking at what the matrices D1 and D2 do. So their products can be rewritten in this way, where X is defined in this way. If one chooses the logarithm of A and the logarithm of B with different signs and to be incommensurate, when S and T vary in the natural numbers, X becomes dense in R. And so we can explore all the values of X. So the other matrix D0 is such that at some point, since it's a rank 1 matrix, it works that at such point, the stationary state will be reset to M0. And therefore, the orbit of the stationary right stationary state, which generates C mean, has to include also the orbit of M0 under this matrix for all the values of X. And now the nice thing is that we can choose M0 in such a way that its orbit is in fact the graph of the exponential cone and the exponential function, and taking the cone generated by it, we get the exponential cone. So we get the first inclusion in the opposite direction. And but the very nice thing is that we can do the same on the other side. So we can choose mu0 such that its orbit gives the dual of the exponential cone. And so this basically finishes our proof, because now we have that C mean is equal to C max, and they're both equal to the exponential cone, which is the only suitable cone, and it is not semi-algebraic. And so there is no quantum model. Okay, so what we have learned from this is that hidden quantum Markov models are expressive enough to model interesting processes, such as the one defined by Fox-Rubin, Damatic-Arian, and Carney, which are not natively quantum. And there is also a gap in terms of memory requirement. I mean, this gap can be robust to noise. However, hidden quantum Markov models are not universal. And so it is interesting to study other possibilities and to study theories which include both quantum models and these other non-semi-algebraic models, and which maybe can be easily characterized. And for example, we have this example of the matrix relative entropy cone, which is able to support both quantum models and and our exponential, our process based on the exponential form. And finally, since quantum and general models are probably more expressively than classical ones, one question, interesting question, if these models can be actually useful for data analysis with data from the real world. And with this, I have concluded, and I thank you for the attention.
Thank you very much, Marco, for this very enlightening talk. I guess we have time for maybe a couple of questions. So I don't see, yes, in the Slack.
Okay, I see.
Andreas is, right. He just mentioned that you have two related papers on these hidden quantum processes.
Yeah. Masaito, I think, just it said to Andreas that we have.
Oh, sorry, Masaito, yes.
Okay.
So
nice.
I have two comments. So indeed, I already discussed similar topic. At least in the same framework, we discussed hidden Markov process, and we evaluated the stochastic behavior. And also we discussed when we have that kind of stationary state, even in the framework of GPT.
Okay, thanks. I will look at it. Yeah.
So if possible, please check our paper, our two paper.
I think we didn't notice it. So thanks. And please link it.
I put if you go to that structure, so you can directly download our paper.
Okay, thanks. What
at least Andreas can access both paper. No.
Nice. What's the are there related results to our?
Yeah, somehow, yes. At least we already discussed in the framework of GPT, and we discussed the existence of stationary process in the framework of GPT. This is one. And also we consider that kind of hidden Markov process. So then we discussed that kind of stochastic behavior. In your talk, you did not discuss that topic, but we discussed that stochastic behavior of that output.
Nice. Yes. We just considered these structural questions, but for sure there are many interesting things to study. Yes, thanks.
Okay, so if there's no other remarks or questions, then let's thank Marco for his talk and